Department of Media Studies, Art and Design at the Lahore School of Economics welcomes you to distinguished guest lecture series. This talk is by Dr. Tariq Abdullah. He is a professor of environmental sciences at Lahore School of Economics. After obtaining his BSc honours from London University and DPhil from Oxford University, he spent 30 years teaching and researching theoretical physics at the MPhil level. Now he leverages his expertise by teaching MPhil courses on climate change and sustainable development at the Center of Policy and Environment.
The title of the talk I'm going to present today is The Great Derangement, and I'm going to talk about how this issue of the Great Derangement is related to climate change. So I'm going to talk about three incidents that took place in the year 2023, last year. Um, the first incident I'm going to talk about is how a light aircraft crashed in the Colombian rainforest. This crash took place on May the 1st, 2023. Surprising thing about this crash was four children survived the crash and they were discovered or rescued almost 40 days after living in the jungle alone and isolated. And so the surprising thing was that 40 days these children managed to survive without any external help. Their mother had died in the crash, the pilot had died in the crash, and they were surprised at this incident of survival. And so one of the questions that was asked is, well, how did they survive 40 days? And the answer actually comes because they were members of an indigenous group, which was called the Witoto group in Colombia. And if you like, the answer actually relates to a kind of strength of the indigenous knowledge or the indigenous education that they experienced as they grew up. So, the relevance to the talk, of the Great Derangement is that this gives us an example of the strength of indigenous knowledge. And for instance, where the social and the natural are both combined in their sort of educational experience. Whereas we're going to contrast this in the Great Derangement with white science or colonial science, which is engaged with the separation of the social from the natural. So this is one incident, an incident that took place in May 2023. The second incident that I'd like to talk about, and which is a little bit relevant to the content of this talk I'm going to give, is the migrant boat disaster in June 2023. All of you probably have heard of this, and this was a boat that sank off the coast of Greece, which was overloaded with more than 400 migrants, and maybe something like 200 of those migrants were Pakistanis. Many of them, died. One of the issues then is when we look at this migration issue, global migration, we find that how are migration or how is the issue of migration or how are migrant numbers controlled? And what we find actually that is these are essentially done by what we can call border controls. The border controls in this case were, the controls of migrants entering Europe, particularly through Greece, and obviously, the other aspect of border controls is the migrants leaving Pakistan, and in order to try and find livelihoods in the European Union. So one of the things that we find is in this example is that the root causes of global migration are not addressed, but the symptoms of global migration are addressed through the issues of border control. So this is the second incident that I would like to talk about, that I'm talking and is relevant to the issue of the Great Derangement. And this is the idea of basically the role of border controls. The third incident that I'd like to talk about is again an incident that those of you who live in Pakistan are very familiar with, the cable car accident that took place in the 23rd of August 2023. This took place in Alai Valley in Battagram in the KP province. And what happened is that in the cable car, two out of three of the cables actually snapped. And so this cable car, or which in local terms is called a dolly, this was left hanging in the air with these passengers, which were six children and two adults. So one of the things, it took about 24 hours for these occupants to be rescued. And how were the passengers rescued? And what we found is that two sort of approaches were followed. The first approach was with the help of army helicopters. And during this 12-hour effort by the helicopter teams, one of the six children was rescued after an effort of something like 12 hours. That operation then was suspended because darkness had fallen. And then the local zipline experts who had, they were actually asked to try and uh, enable the kind of rescue to continue during the night. And these were actually two people, Nasir Khan and Sahib Khan, locally known as the Khan brothers. And they actually managed to rescue the remaining seven passengers during the night. Okay, so how is this story relevant to, again, this issue of the Great Derangement, which I'm going to talk about? What we find is that this seems to represent, the indigenized technology of the local zipline experts were able to rescue seven out of the eight passengers. Whereas in the first attempt, during almost 10 or 12 hours of efforts, the helicopter teams, which were using basically imported technology in terms of helicopters and winches and things like this, they were only able to rescue one child. So what we see is sometimes, the example, the lesson that I want to emphasize is the strength and weaknesses of different technologies, a kind of indigenous technology and a kind of imported technology. And so this is the kind of issue that we will try to cover as well in this talk on the Great Derangement. Okay, so those three examples, the example of the crash in the Colombian rainforest, the example of the migrant boat disaster off the coast of Greece, and the third example, the cable car accident in Battagram, these sort of represent some of the kind of issues that we are going to talk about in the Great Derangement. So let's move on then to the talk itself. And the slide here, illustrates the Great Derangement, the title, and its relevance to climate change. And it was originally a talk presented in LSE in October last year. Okay, so the first question that we will perhaps need to look at is what is meant by the Great Derangement. And basically, the issue is, let's say, the issue of the Great Derangement has been brought to a general public audience through the historical novel of Amitav Ghosh. And we can read this in the slide. The historical novel was written by Amitav Ghosh, and it had a subtitle, the novel, of Climate Change and the Unthinkable. And this then introduced the term the Great Derangement into more popular use. The second example of where the Great Derangement has been used is in a journal article that is in the journal called Climate and Development. It was published in 2019, and it had the title Beyond Technical Fixes, Climate Solutions and the Great Derangement. So this also used the term the Great Derangement as a kind of way of framing the issue of climate change. So what is the common feature then of the Great Derangement? And the Great Derangement is basically an expression of dualism, the separation of nature from society, and in particular in terms of climate change, it's the separation of the climate drivers, the social drivers of climate change from the natural drivers of climate change. And this is what we call the Great Derangement. What I'd like to do is to look at climate change policy as a kind of expression of the Great Derangement. And so what we can do is we can try to look at, there are two basic organizations, global organizations, which are concerned with climate change. One is the Intergovernmental Panel of Climate Change, the IPCC, and this prepares a series of assessment reports. The first assessment report was presented in 1990, and the most recent assessment report number 6, was presented in 2022. The IPCC also was awarded the Nobel Prize in 2007. The second organization that is related to global climate governance is the United Nations Framework Convention on Climate Change, known as the UNFCCC. It was established in 1992. It has undertaken a series of conference of parties, starting from Berlin in 1995 and ending with COP27 last year in Sharm el Sheikh and COP28 in Dubai in 2023. Okay, so these have been, these organizations, the IPCC and the UNFCCC, both have, perhaps we can say, strengths and weaknesses. But the thing that I'd like to point out, and we'll do this in the next slide, is that 30 years of efforts have not been able to reduce carbon dioxide emissions into the atmosphere. And here we see a picture of global fossil fuel emissions starting from the year 1960 and going up to the year something like 2020. And what these are actually, these are annual emissions of carbon dioxide, essentially produced by the burning of fossil fuels. And what we see in the 1960s, the amount was something like 10 gigatons of carbon dioxide per year. And what we see is by the time we reach 2020, the amount of carbon emitted into the atmosphere has approached something like 40 gigatons of carbon dioxide. It has increased. In spite of the fact that from 1990 to 2020, there have been actually 30 years of efforts at climate mitigation. And if we look at this particular curve, we see that there are small dips in the curve. There are dips, but each of these dips, the first one with the oil crisis, the second one with the second oil crisis, the third one when the Soviet Union collapsed, the fourth one with the global financial crisis of 2009, and then the last dip we can see is the COVID-19 dip in 2020. So what we see is that these economic recessions have affected this global fossil CO2 emissions. But the efforts at climate mitigation have not been able to bend the curve. In other words, to reduce the amount of fossil fuel emissions which are entering into the atmosphere. And mitigation is basically, the attempt to reduce this and to basically, begin to bring down the levels of fossil fuel emissions from 40 to lesser amounts. And this is, so we can see that there is a kind of failure. And one of the issues is, why is there a failure? And the argument of this, this particular talk is, this is because the social has been separated from the natural. In other words, this is an expression of the Great Derangement. Okay, so I'd like to then move on maybe to the next slide. And in the next slide, I would like to look at, the relationship between science and knowledge. And particularly, I'd like to try and explore how, modern scientific knowledge and maybe traditional or vernacular knowledge have their own particular strengths and weaknesses. So first of all, if we look at this, we can understand that all knowledge comes from experience and reflection on that experience in the light of previous knowledge. But how does modern scientific knowledge compare and contrast with traditional knowledge? And if we look at modern scientific knowledge, this really has become a kind of industry, and in which we have scientists who really express a kind of community and a kind of expression of the division of labor, so that they are particularly scientists are then part of this, we could say the industry of science. Whereas, what we find actually is that different modes of knowledge, have have particular strengths and particular weaknesses. And so let's try and explore in the next slide the sort of one of the aspects of the dual character of science. We see that there are two contrasting aspects. One is that science is sometimes characterized as universal in character, and it's presented as the incremental accumulation of scientific knowledge. And the second aspect is that science is a social product. It is characterized by the social conditions of its production and the perceptions of the owners of that scientific knowledge or the producers of that scientific knowledge. In other words, science is an industry and reflects the interests of the owners. So here what we have is two maybe contrasting aspects of science: the universal character, which almost presents it as almost independent of the social context, and its characteristic as a social product, and in the sense it's the characteristic of science as being a kind of contingent product. Okay, what I'd like to then address is how the framing of climate knowledge results in concealment of ways of knowing. In other words, how does an image reveal some aspects and hides other aspects? And particularly, what kind of aspects does it hide and what kind of aspects does it reveal? These kinds of issues have been explored in two particular articles that I'd like to refer to. One is a Nicholas Hildyard article written in 1995, when he looked at and he gave the title "The Planet as a Patient." And the second example was an article written by Larry Lohman in 2008, which was entitled "The Production of Ignorance in Carbon Trading." So obviously, here what he's suggesting actually that a lot of carbon trading knowledge actually results in the production of ignorance, which is something that maybe appears to be rather counterintuitive. But so the issue that I'm trying to explore here is, the sometimes what we call the co-production of knowledge and ignorance. That sometimes we explore when we produce knowledge at the same time, we perhaps also uh, raise more questions and increase our ignorance in some way. And this kind of issue is sometimes called the co-production of knowledge and ignorance. Okay, so I'd like to then, this up to now, what I've talked about is a little bit about a comparison of the different ways of knowing nature. Particularly, I've tried to focus on the relationship between modern scientific knowledge and indigenous knowledge, traditional or vernacular knowledge. What I'd like to move on to is to look at the global institutions that I introduced at the beginning, the IPCC and the UNFCCC. And just to maybe repeat what I've already said, is which global institutions have enabled the advancement of climate change. In the introduction, then I mentioned the IPCC, which produces which focuses on the scientific evidence and produces these annual assessment, not annual, but almost 5 yearly assessment reports. And the second global institution was the UNFCCC, and particularly this is known for organizing the annual Conference of Parties, which are meant to decide global policy on climate change. So what I'd like to talk about, and we'll explore this in the next slide, is the nature of these global institutions. And particularly, I'd like to start then with the IPCC. We can raise the question of how does the IPCC work? And in order to illustrate this, I'm going to quote, from the IPCC 2013 uh, uh, report, which says underlying all aspects of our report is a strong commitment to assessing the science comprehensively, without bias, in a way that is relevant to policy, but not policy prescriptive. So when we look at this, there are four aspects that I'd like to sort of explore in more detail. The first aspect is, the science. The second is, the aspect of science being to be comprehensive. The third is the nature of science to be science without bias. And the fourth is, the aspect of science as being policy relevant, but really not policy prescriptive. So I'd like to explore these four aspects in a little bit more detail in the next slide. Okay, so to first look at the first aspect, about the science, notice the definite article. This points to a kind of singular character of science and neglects ontological pluralism. Science is a black box, independent of its contingent and contextual character. The second aspect, which was the aspect of science being comprehensive, suggests that gaps in scientific knowledge can be filled by more science and are not structural in character. Mike Hume, in an article in 2018, actually questioned this kind of incremental assumption about how science can be comprehensive. And the third aspect is interesting, is the idea of science being without bias. And this suggests that climate change is not driven by science for profit, and is rather driven by the science for people's needs. And here, the issue really at the focus of this is, are there beneficiaries and sacrificial zones in climate change? Are there aspects of science which, are biased in favor of one or the other kind of aspect, as, science for profit or science for people's needs? If we go to the last aspect, this is the relevance to policy that is talked about in the IPCC commentary. Here, the description here is policy relevant, but not policy prescriptive. The characterization is interesting. How can policy really be neutral with respect to class interests? Here, climate is both representable by knowers removed from politics, and it is also manipulable by controllers who are advised by the knowers. And so who are the knowers? The knowers are the IPCC, who summarize the scientific aspects of climate change. And who are the controllers? The controllers are basically the conference of parties, which are then meant to decide, the policy arising out of climate change. Okay, next. In order to give an idea of how this, what is the nature of science, it's maybe useful to take a kind of quote from Sir John Houghton. And Sir John Houghton was the founding member of the IPCC, And he gave an interview explaining that UN climatologists were not permitted to mention the carbon locked up in fossil fuels in their analysis of climate change, but only the carbon that has become more mobile in the form of carbon dioxide. This was an interview that was given to Marshall in 2014. To follow what happens when carbon atoms cross one of the internal boundaries of the Earth's geophysical system into the atmosphere is science, Houghton said. But to analyze their movement towards that border is not a science question. So here, Houghton was actually describing, what is science and what is not science. And this actually description actually is quite illustrative. This is in the basis of then the kind of analogy that I was trying to present at the beginning about an analogy between climatology, the science of climate change, and the issue of global migration. And what we find actually is that climatology and global migration are both framed in a similar manner. Both are framed as border control issues. Both perspectives address the symptoms rather than the root causes of their particular problem. Fossil fuel burning is the root cause of climate change, and the global north-south divide is basically underlies the global migration issue. So these are the kind of root causes and what we find actually is that both climatology and global migration, then because of the framing, they tend to end up as addressing only the symptoms rather than the root causes of their own perspective issues or questions. Okay, so this is so what I'd like to do is to maybe, we've talked a little bit about how the IPCC works, and we've talked about, what I'd like to talk a little bit about is in the next slide, how the UNFCCC, the Conference of Parties or COPs, what are the unwritten rules that but really determine the conduct of these COPs. And here I'm going to just summarize, in the slide here, I'll read out under these rules, scientists at the IPCC inform policymakers that climate change is not about labor, capitalist mechanization, or fossil fuels, but about CO2 molecules being in the wrong place at the wrong time. Policymakers then agree to disagree how to ride herd or control on all of these rogue molecules, carefully avoiding the issue of capitalism, work, or oil companies. In both cases, climate change action becomes organized around the alienated objects of wayward CO2 molecules, in the same way that far right politics is organized around the fetishist figure of the immigrant. Inquiry into all the different ways that capital accumulation is related internally to climate change, while not explicitly forbidden, is implicitly discouraged. Instead, the focus is on carbon budgets, just as the focus of right-wing governments is on immigration budgets. So these are some of the aspects of the unwritten rules of the IPCC. So what I've tried to look at up to now is the role of the IPCCs and the UNFCCCs. What I'd like to do now is to move on to a second aspect of this talk, which is how physics has impacted on the social. In other words, how physics, as an example of the study of nature, has impacted on the social, the way in which societies are structured through the development of thermodynamics. And this will illustrate some of the issues that are underlying climatology. So first of all, what I'd like to look at is the first law of thermodynamics. This is sometimes called the law of conservation of energy. And what students are probably familiar with is that Energy is never created or destroyed, but it is only, you know, it is transformed from one form into another form. This is particularly true in the biogeochemical processes that take place on Earth. Obviously, uh, when we look at other physical processes in nature, we do find that matter can be converted into energy, etc. But here, as far as the biogeochemical processes, these are all in processes of conversion of energy from one form into another form. So another way in which we can describe this first law is in terms of conversion equivalences. In other words, one of the things that we learn when we study physics at school maybe is that heat and mechanical energy are different forms of energy. And we talk about, the equivalence between heat energy and mechanical energy. And maybe, and similarly, we learn about these conversion factors when we look at this. And what we find actually is that in the 19th century, these equivalences between different forms of energy were established between many different forms of energy, between heat, mechanical, electrical, electromagnetic, and many other forms of energy. And practically, these conversion engines were invented by physicists in the form of steam engines, generators, motors, light bulbs, petrol engines. All of these are basically forms of conversion engines. So this is the nature of the first law of thermodynamics. And, and basically, what we find actually is that the best way to understand maybe the first law of thermodynamics is in terms of these processes of conversion of energy from one form into another form. Okay, this process of conversion of energy uh, is in effect a kind of process of commodification. In effect, the first law of thermodynamics helped untangle heat and mechanical energy, electromagnetic and chemical energy from their previous social and natural context, showing how they could be combined and exchanged with each other to form a single liquid commodifiable whole that could be circulated, aggregated, and subdivided. In so doing, it helped open businesses' eyes to the possibility of a flexible production that did not need to assume, in the words of one historian, a fixed limit on the forms of energy that could generate work. Not only the human body, but all of nature itself became a machine capable of producing mechanical work or labor power. Work, it now seemed, might be wrought from anything. So this is the idea of, the equivalences of energy that were discovered and realized by from the first law of thermodynamics. They have actually enabled this kind of commodification of energy. We can look at this conversion process as the invention of what we can call abstract or big energy E. Okay, so what is the aspects of this invention of abstract energy E? Energy, as I said, was, from the first law of thermodynamics, has become a kind of fungible resource. In other words, it has been able to, it has, it has enabled energy to be converted from one form into another. Energy could be converted or transformed from heat into mechanical energy. It could be converted from mechanical energy into electrical energy. Chemical energy could be converted into electrical energy. All these processes of conversion were enabled by this first law of thermodynamics. Energy was commodified, which really means that there is a kind of process of enclosure of energy. Energy was disentangled from its previous context and re-entangled in a new context. This is what we mean by the process of enclosure. Vernacular energies, or indigenous energies, were historically entangled in their particular environments. So we find that vernacular energy is in the form of water mills in rivers, windmills, sailing ships, which were using the trade winds, biomass, which employed, wood or the forests, the burning of forests, the smelting of ores near the mines of different ores. These have all been described as vernacular energies. And these vernacular energies were all different and were all separate. This was the nature of. If we then, in the next slide, we look at this process of the invention of big energy, we can characterize it by this picture here. And what we see is that big energy, this big red arrow, represents the kind of magnitude of big energy E. And what we find is it also represents, the way in which, uh, as this big energy E comes out from a process of the enclosure of vernacular energies, the multiple energies of vernacular energies are shrinking in magnitude, whereas big energy is growing in magnitude. So one aspect of this big arrow is as we move from left to right, we are, seeing the expansion of big energy. The other aspect that is shown in this arrow is that we have some aspects which are above the arrow, which we can call are the front story. These terms above the arrow are these are things like the innovations that gave rise to the establishment or the discovery of energy. And the issues below the arrow are sometimes what we call the backstory. And these backstories are basically the process of resistance to the development of big energy or the commodification of energy. So what we find is above the arrow is the inventions or the kind of discoveries that appear in popular descriptions. And what we find below the arrow is the less known aspects of the development of big energy, which is the resistance in various forms. And we can see these kinds of resistances in the form of Luddites, for instance, their movements, and we can see, the aspects of the front story in terms of, the invention of thermodynamics and, the conversion engines. We can also have a look at, what are sometimes called the persistent conflicts between these two forms of energy, between big energy and the vernacular energies in plural. And here, if we look at this, if we look at this kind of persistent conflicts, what we find actually is that there's a number of issues that are explored. There's the issue of scarcity, there's the issue of autonomy, there's the issue of what kind of energy enables surplus to be accumulated, and what are the roles of safety nets. We find over all of these issues, we find that, let's say to look at the first issue, that from the perspective of big energy E, you know, big energy is always going to be scarce. Whereas from the perspective of vernacular energies, what we find is that, the scarcity is a kind of product of the social context. And, that there is, that in the terms of vernacular energy, scarcity, the use of vernacular energies is self-limiting. So it doesn't really raise the issue of scarcity in the same way. Similarly, if we look through this slide, we can look at other aspects, the aspects of autonomy, the aspects of how surplus can be generated, etc. And these are then some of the persistent conflicts between big energy and the multiple vernacular energies. What is the second law of thermodynamics? In terms of physics, this is related to the idea of entropy, which maybe is something that maybe is a little bit difficult to understand. But it also, let's say, it gives rise to sometimes, the idea of irreversible change. In other words, Time has a particular direction and time cannot be reversed. The aspect of the second law of thermodynamics that I'd like to explore in this particular talk is that when we look at these processes of conversion that have been enabled by the first law, these, these processes of conversion always lead to the degradation of energy. And what we find actually is the second law of thermodynamics basically says that the amount of usable energy declines with each conversion. And it's this aspect of the second law, that I'd like to sort of talk about, is the relationship between, if you like, what we will call useful energy and degraded energy. If we go on to the next slide, a kind of illustration of this is given in this diagram here of US energy consumption in 2021. And it's shown as what is called a Sankey diagram. If we look at this Sankey diagram, what we see on the left-hand side is basically the sources of primary energy. And what we see on the right-hand side actually is, sometimes what is called, the useful energy and the degraded energy. What we see is the primary energy are given in different colors, yellow, red, blue. These refer to different kinds of primary energy. And what we find here on the right-hand side is, the two, the gray box here on the right hand shows the wasted energies, whereas the dark gray box below it shows something like the useful energy that is produced. And what we find actually here is that the interesting thing is actually the light gray box is much larger than the dark gray box. In other words, the amount of wasted energy or degraded energy is actually much larger than the amount of useful. In the case of this Sankey diagram, this is called useful energy is called energy services. So here the Sankey diagram itself you know illustrates this idea of the magnitude of the degraded energy or the wasted energy that is related to the second law of thermodynamics. And we can see as we look at each of these diagrams, we will look at this Sankey diagram if we go through it from left to right, we can see how the amounts of useful energy in the dark gray are actually a kind of small fraction compared to the amounts of degraded energy in the light gray arrows. Remember, in the Sankey diagram, all of the flows are the magnitude of the flows are given by the width of these arrows. And so we can see the different we can see the different contributions of the different forms of primary energy, how they contribute to the production of energy and the production of electricity, etc. Okay, so this is then an example which shows the uh, the nature of the second law, particularly the way in which I wanted to describe it in terms of how useful energy, how energy is created, enables useful energy to be created, but at the same time also results in degraded energy. And how this degraded energy is described in physics is described as a kind of increase in entropy. How did capitalism respond to these two laws of thermodynamics? And so, first of all, what I'd like to look at, how did capitalism respond to the first law of thermodynamics? And if in this next slide here, we see that capitalism responded to the first law of thermodynamics with considerable enthusiasm. The need for energy to run machines and enable capital accumulation seemed to be limitless now. This energy was obtainable from a variety of natural resources, and it's the ingenuity of science and capitalism to enable these kinds of conversion engines to be realized. So we found, that we can produce energy from wind, water, sunlight, fossil fuels, biomass, and nuclear. This next slide illustrates then the 50-pound note from the UK. And here what we see is a picture of, on the left, of Henry Bolton, an entrepreneur, and on the right we see a picture of James Watt, who was the inventor of the steam engine. And the interesting thing is the quotation that is given. Mike Bolton, he characterized, he says, I sell here what all the world desires to have, power. And so this sort of illustrated the kind of enthusiasm of the entrepreneur as a result of the development of the science of thermodynamics. And here on the right hand side, what James Watt says, I can think of nothing else but this machine. He's referring to obviously the steam engine, the machine that he was credited with inventing. And so here what we find is that we can see in this picture of the 50-pound note is the kind of combination of interest between the capitalist Matthew Bolton and the scientist James Watt. We've talked about the first law as generating a lot of enthusiasm for capital accumulation. Let's move on to the second law. And how did the second law have applications for capital accumulation? Okay, the second law, as I mentioned, during each process of a conversion engine, energy was degraded and made unavailable, to run machines. So this meant actually that we continually needed new frontiers of energy extraction. So continually, capitalists had to search for new frontiers in the form of tar sands, in the form of fracking, in the form of coal gasification, etc. And so what happened actually there is, if when we look at this, the first law helped capital create a world of limitless fungible resource, or if you like, enable capital to see a world of perpetual growth. The second law exposed the other side of the picture. What I've tried to do actually is to talk about a summary of the first law of thermodynamics and the second law of thermodynamics and its relationship to the rise and fall of capitalism, how it has enabled or maybe threatened capital accumulation. So this is what I've tried to do when I've looked at these issues of the physics, particularly of climate change through thermodynamics. So what I'd like to do actually is to move away from this focus on physics to come back to the idea of climatology or the study of climate science. And so let's say if we revisit this issue that I introduced in the beginning, climatology is what is taught in a course on climate change. And climatology is based on the separation of the natural from the social. It is about managing carbon, which has entered the active part of the carbon cycle. It does not address the question of why fossil fuels are burned, what drives this process of extraction and burning. So this is the nature of climatology. We can try to explore this question of how does climatology address the climate problem. It views the climate problem from the perspective of the management of errant carbon molecules in the atmosphere. This narrow perspective focuses on the management of carbon and the carbon budget. This is the perspective of many climate movements and organizations. And here, this is then a focus on the role of carbon. What I'd like to do is in the next slide, I will try to how to contrast, how climate movements and social movements differ on the way in which they view the climate problem. And so in this slide, I'm exploring a little bit about how do social movements view the climate problem. In the In the past slide, I was talking about how do climate movements view the climate problem. So the social movements adopt a much broader perspective on the climate problem. They resist extractivism in all forms. They defend, the sacrificial zones that have been made popular by Naomi Klein. They defend indigenous rights, and they engage in local struggles to defend livelihoods. They engage in resistance to enclosure. They try to build new commons and defend the existing commons. These are how the social movements view the climate problem. Climatology then has, certain, what I'm arguing is have certain political biases. Dialogue about the political biases of climatology, particularly when focused on the IPCC, is more difficult than dialogue about the political biases of, of policymakers that are reflected in the COPs. So what I'm arguing here is that when we look at the Conference of Parties, we can see the kinds of political biases which are expressed in the dialogues over climate policy in the Conference of Parties. But sometimes when we look at the work of the IPCC, it looks as if the doesn't have political biases, like it was claimed in the framing of the IPCC. The IPCC works, without bias. So what I'm arguing actually that climatology engages in a kind of it makes climate science or climate change a kind of border issue, a kind of border control issue. And so the IPCC also engages in this incessant border controls about the discipline of climate science. And it's these border patrols that are not immediate sort of visible. They are, in the sense, these kinds of political biases to a certain extent remain hidden. And it's these political biases of the IPCC that I'm trying to address by looking at the issues of the physics of thermodynamics and their implications for climate change. Um, we can try to look at, what is the dominant view of energy. And industrial capital sees energy as a substance that must be constantly replenished because it is running out. Hence the need for more oil fields or more sites for dams or more wind farms or solar farms to provide society with more of this resource. So this is the dominant view of energy. But we can contrast this with a view of energy basically as a kind of process, not as a substance. In other words, we've tried to talk about energy as a process of conversion of energy from one form to the other. So the one perspective or the dominant view of energy is energy as a substance, but a more maybe a better way of looking at energy is in terms of energy as being a kind of process, a process of particularly conversion, engaging with the conversion of energies from one form into another. And we can explore then what are the needs of industrial capital. Industrial capital expands and intensifies its exploitation of labor through machines. It needs machines to boost productivity, control and concentrate workers, spread the labor relationship in society, accelerate the turnover and appropriate new feedstocks. This is the kind of need. From capital's point of view, this is what all these power stations, hydroelectric turbines, and even interpretation machines are for. Machines do not consume energy, but convert it from one form into another. So these are the needs of industrial capital. The kinds of developments of digital capital have sometimes been described, as interpretation machines. And digital capitalism then has a long history going back to the issue of scientific management that was developed by Frederick Taylor in 1911. The the issue of industrial capital, or was also elaborated on by Harry Braverman in his work on the degradation of work in 1988. And more recently, we have the buzzword of artificial intelligence, which is, again, a kind of form of digital capital. What's common to all of uh, these interpretation machines actually is almost the relationship between living labor and dead labor. And dead labor then is what epitomizes, the nature of capital. So energy conversions can actually be viewed as falls in entropy. The only difference normally when we think of a fall, we think of a fall as being from high to low. In the case of entropy, it's the opposite. You know, energy conversions engage in entropy, but the flow is from low entropy to high entropy. So here, if we look at the idea of, you know, where are these kinds of falls in entropy to be found? We can find them, obviously, the most easiest example to understand is, the role of hydroelectric power and dams. And what we find here is the potential energy of water, which is basically gravitational energy, is converted into mechanical energy of the flow of water. And this conversion into the flow of water then results through a generator in the form of generation of electrical energy. The fall of water is a gradient of entropy. And what we have is the entropy, in the form of water at a higher gravitational potential has lower entropy, whereas the water that results as a consequence of conversion ends up as a higher entropy. And this fall then we can see in the conversion engine of a dam. There is this gradient from, or the fall of entropy from low entropy to high entropy. What are these gradients in entropy and where are they found? And sometimes this issue is then sometimes is also called a Carnot landscape after the physicist Sadi Carnot, who did a lot of work on the second law of thermodynamics. What capital needs for its machines is not energy as such, but these falls in the landscape, differences between low and high entropy, the gradients between a hot and cold in a heat engine, the gradients between the binding energy of electrons in molecular bonds and the heat generated in chemical reactions, the gradients between short wavelength solar radiation at around 5,760 Kelvin and the longer wavelength radiation emitted by the Earth at 250 degrees Kelvin into outer space, which the outer space then, has a temperature of something like 2.7 kilo Kelvin, and so on. When capital burns oil or runs radiation from the sun through solar panels or runs industrial biomass plantations, it doesn't use up energy, but rather pulls up or opens various doors, usually violent, through which an entire territory can slip more rapidly down these gradients, eroding the gradient itself in the process. This is sometimes, as I've mentioned, is called a Carnot landscape. And in the next slide, then we can try to explore a little bit more about how is entropy released, and particularly, entropy is released by the way in which these doors are open and closed. And particularly, the sequence and patterning of the door opening has to suit the operation of capital's conversion engine. It's no good having a sluice gate if you can't open and close it at the right times. There's no use of having coal if you can't apply heat and oxygen and vent carbon dioxide in rhythms and places that fit your machine's functioning. Whatever, the more intensively capital converts energy from one form into another, the higher the entropy of the system. And if that system is closed, the closer that entropy change comes to halting altogether. So it is this entropy balance that sets a limit to the power of the engine. The hierarchical landscapes of multiplying first law conversion engines are also landscapes of increasing second law waste. These, of course, are also hierarchically organized in the form of relationships between energy beneficiaries and sacrificial zones. So this is the idea of, if we move to the next slide, we can explore, this is the idea of the opening and closing of these entropy doors. I think just to illustrate this example a little bit more is to give you an example of this, of a kind of entropy door and how it is opened and closed. So for instance, if we take a flask of hydrogen and oxygen, and we have hydrogen and oxygen both existing in a flask, hydrogen and oxygen can continue to exist in a flask almost in forever. It can continue. The only thing is that when we introduce an activation energy, which enables the hydrogen, when we introduce a match into the flask, which will then ignite the hydrogen with the oxygen, then we release, we burn, hydrogen and oxygen, which existed in a lower entropy state, will then be converted into water, which exists in a higher entropy state. And how is this conversion done? It is done through the process of essentially activation energy. In other words, the process of, in the case of this particular example, of igniting a mixture of hydrogen gas and oxygen gas in a flask with a match. And so this is, putting a match there, or providing the activation energy for a process to take place, is basically opening the door for an entropy fall. So opening the door for an entropy fall then involves, if you like, in more technical terms, this supply of an activation energy, which then enables the release of considerable energy through the fall from from low entropy to high entropy. These entropy chains then really relate useful and wasted energy. So these chains only multiply overall entropy increase. In coal-fired generating power stations, something like 60% or more of the fuel's chemical energy is lost as waste heat. An additional percentage of the electrical energy is generated is then dissipated into heat in transit. For instance, in terms of the supply through the electricity grid. Then sometimes what happens is when we look at, even if we look at the most up-to-date efficient light fixtures, these lose at least 20% of the electrical energy feeding them. Their light is then partly downgraded into heat on contact with, say, a billboard on an empty street at night. So this kind of, the creation of useful and wasted energy, we saw this more vividly in the Sankey diagram, about US energy consumption in 2001. So when we look at these entropy chains in the next slide, what are these entropy changes and how are they structured? Capital typically structures its unprecedented entropy increases in chains. Before hydroelectric dams and turbines can go about their entropy increasing businesses, entropy increasing concrete and steel manufacture has to take place. Entropy increasing wind farms can't be built without previously entropy increasing balsa extraction in Ecuador and other countries. Rising rates of entropy increase associated with the movement of electrons in millions of electric cars in the global north stem not only from the prior construction of dams and wind farms and other energy conversion devices, but also from the new waves of entropic lithium and copper extraction in Atacama and elsewhere. So what we find is that these entropy chains are involved, what we in environmental studies we call life cycles, and it's these there's a kind of chain there's a kind of chain of processes in a life cycle that determines, the nature of these entropy changes. We can then, really see how, these entropy chains, result in a kind of description of a kind of entropy landscape, or which uh, some people have called a Carnot landscape. So entropy changes results in the gradients in entropy being removed in each conversion process. One process has upstream processes as well as downstream processes. This becomes a chain of processes. These chain of processes create a landscape. So it's a little bit like an industrial food chain. Like the industrial food chain creates a kind of an industrial food landscape. Similarly, what we find is that these entropy changes then create a kind of landscape of entropy change. And these entropy chains are a little bit, as I've mentioned, like a kind of life cycle analysis. They involve both upstream processes as well as downstream processes. Let's try and come to the kind of conclusion that we can arrive at from this kind of analysis. We've looked at various aspects of the climate derangement. We've looked at, in terms of, the functioning of the different global organizations, the IPC and the UNFCCC. We've looked at the role of physics in determining the social aspects of on the impacts on society, and particularly on the impact on capital accumulation. We can try to, as a kind of conclusion, we can try to come to the kind of question, what makes the world go round? And the answer to this kind of question is, sometimes people say that energy makes the world go round. Sometimes people say that money makes the world go round. Here, what we're presenting in this kind of analysis is that really that entropy chains actually, enable the world to go round. In other words, to processes of capital accumulation, and enable the way in which living labor is then, dominated by dead labor in the form of capital. So how are these entropy doors opened and closed in different territories, resulting in entropy flows and the export of entropy? How are these doors opened? By whom? For what? Why? And with what effects? On whom and where? This is why we need to understand something about the history of energy. And what this article has tried to do, or this talk has tried to do, is to look a little bit more at the history of energy. Or, if you like, we can say we've tried to look at the invention of the concept of abstract and big energy E. Oh, the last slide here. So, as I've mentioned, we've tried to look at, the lessons of this analysis have been something about the relationship between the IPCC and the UNFCCC, the role of physics in capitalist development, and the need for climate justice perspectives based on a Carnot landscape and indigenous knowledge. And this is then related to, the negation of the great derangement. In other words, the reintegration of the social with the natural is needed to really address the issue of climate change. So the last slide here, refers to some of the references of articles that really explore the kind of questions that I've raised in this talk here. And we'll conclude with that. Thank you.